Okay, it is started. Now, what I'm going to do here is if I click on this worksheet link here, it's going to download a copy of the worksheet. I will save that in a temporary folder, and then I'm going to open that inside of RStudio on my machine. So hopefully all of you have at least been able to install a version of R, preferably with RStudio on your computer, and have it working. Can anybody please let me know right now if you have not done that yet, and if so, we can help make sure everyone is at that point. Does anybody not have RStudio working right now on their computer? Hearing no objections, I will go ahead and open RStudio here. Now, you may notice that your RStudio might have white text or white background with dark text. I think that hurts my eyes, so I have just changed the settings to have dark background with light text. But other than that, the configuration on our machines should be pretty much the same. So just in case you were worried that it doesn't look like yours. So now, the way I would recommend going about this is go and once you've downloaded that worksheet file, you can open it. I put it in this temp folder. So now it's open. Okay, so if everybody can just go ahead and do that. And before I start the intro slides, we'll just make sure we're all on the same page. So everybody just go ahead and open this worksheet in your RStudio session. And please raise your hand or speak up if you're unable to do that for whatever reason. Okay, I see some thumbs up. Awesome. Okay, well, I will, while folks are doing that, I will go ahead and start a bit of an intro, a few slides before we actually get started on some hands-on coding, but I'll try to give you the big picture of what we're doing and why. So going to the slides here. So this is what we're going to do today for the first two lessons are kind of, I call it the R boot camp. What we really want to learn is we want to learn statistics. We want to learn how to work with data. Obviously, in this day and age, that requires software. So we need to have some kind of software language that we can use to tell the computer what it is we want it to do. And for this, we're going to use R. I'll talk a little bit about what that is in a minute. Yes, I pretty much went over this already. Again, we're going to be following along the slides, fill in the blanks as we go, and run the code. And yeah, again, I guess the other last note that I was going to make is that I'm not purporting to teach you, everything there is to know about statistics. This is kind of more of an applied thing. So we're going to kind of learn how to do stuff, a little bit of the why and the theory behind it as much as I can, but obviously that's whole semester's worth of material. So we may gloss over some of that stuff, but feel free to ask questions about that as they come up. Here are the learning objectives for the first lesson. We want to learn what is R, what can you use it to do. We're going to type in some commands in the console and run those commands and have R do stuff that we want it to do. We're going to learn about data types, what kinds of objects, essentially data objects, the R statistical programming language works with. And we're going to learn a little bit about statistical distributions in R, and we're going to learn about packages. Okay, so what is R, and also what is RStudio? Well, they're basically software tools that are designed to work with and analyze your data, to generate statistics from data. And R is actually a programming language. So like all languages, it has a grammar and a syntax and a vocabulary, and it is used for us to tell a computer to do certain commands. And it was written by statisticians, so it kind of specializes in things having to do with statistics. Like other programming languages like C or Python or Java are more general, but R was really started for doing statistics. It can do a lot of other stuff too, but that's kind of how it got started. And it is a free software. It's open source, so you can see the source code that was used to create the R language, and anybody that wants to can write packages and contribute them to a central repository online where people can then download them and use them. And packages are like collections of code that do a specific task that can then be used by anyone. So anybody can contribute a package. So it's buyer beware in some cases, right? Like not just because a package is out there doesn't necessarily mean it's right and everything about it is good, but just like other things on Wikipedia model, the good quality ones are vetted by the community of users and rise to the top. And what is RStudio? Well, RStudio is like an interface, a tool to help you write and run your R code. It is not R, it is an interface for R. So if you just like downloaded RStudio onto your machine, it wouldn't work unless you also downloaded R. It's just a front end. R is doing all the computing of number crunching in the back end, and RStudio is just an easy, convenient way to work with it. You don't have to use RStudio. Other people like to use Positron, VS Code, other things as their sort of interfaces, but I've kind of got started using RStudio a long time ago, so that's what we're gonna be working with. So are there any questions so far? I don't want to get too far ahead of things. Excellent. So this might make more sense once I show you the different. When you open RStudio, there's going to be different. The screen is divided up into little regions that they call panes, and each of the panes has a different function. And so there's the console, the scripts, the environment, and the one that has the files and plots in it. So let me just switch screens to RStudio. So you will put it on a full screen. There we go. And so you can see here in the lower left, by default, you can move these around, but by default it's going to be in the lower left. This is the console. This is where we enter individual lines of code and execute them and see what the results are. The output will appear in this console as well. This one on the upper right is the environment. Mostly it is used for showing what variables have been defined and are available for you to use right now. So like where the objects that are storing the data. Right now it says environment is empty because I just started a fresh R and don't have any variables loaded in the environment yet. Since I just opened that worksheet, it will appear in the scripts area of the pane, and you can see that you can have multiple scripts open at once, and they get little tabs up here. And all that scripts are is a text file. It's just a plain text file, but it's not a .txt file. It's a .r file, which tells, it's just still a text file, but that's just indicating that there is R code in that text file that can be run by the interpreter, sort of like the program that executes the R code. Just a text file. And I highly recommend always any important code that you ever want to use again, don't just type it into the console and run it one time. Type it into a script and save it, and then it can be run again exactly the same way in the future, which is very important for reproducibility. That's what makes scripted tools better in many cases than like a point and click one, because it's harder to, you can have that script that you can then run identically in the future and reproduce the same analysis the same way, which is not as easy to do with a point and click convenient though they might be. And then, yeah, the last one in here, this one has a bunch of tabs. It's got your, files. You can open files from here. If you make a plot, a graphic, it will appear here. And also help, if you can call up help documentation on different parts of the R code, and it will pop up there. Okay. Let's talk about what are some of the objects that we're going to be interacting with and manipulating when we write our code. Well, there's two main things, variables and functions. Let's talk about variables first. A variable is a structure that holds data. And an example of a variable would be a vector of integers, of numbers, essentially. C is a function in R that defines a vector, so like a list of objects, and a list might just be individual integers like 1, 2, 3. A character string, so data in R does not have to be numerical data; it could also be text, and we call those character strings in R. And you can tell when you have a character string because it has quotes around it. Another variable would be a data frame. Data frame we'll talk about more later, but that's R's most common type of data in table form. Any data structure that has rows and columns, basically, and different, each column having a different data type. So that whole thing is a variable. The other one, I said there's variables and functions. Variables are kind of like the nouns, the objects. Functions are like the verbs of R. They take input, do something to that, and then give you output. We call the input the arguments, sort of like a computer science term. Functions could just be like simple mathematical functions, right? Like log is the natural logarithm function. It takes a numerical value as input, calculates the natural log, and gives you the output. And you can see that functions always have a name and then parentheses surrounding their inputs, their arguments. So log parentheses 10 means take the input 10 and do the log function on it and give me the output. That's what that means. Functions can also take multiple inputs, like the C function, standing for combine, will take multiple inputs and make a vector, a sort of concatenated list of those items or objects as the output. So the C parentheses, if you have multiple arguments, you always put commas in between them. C1, 5, 6 will take those three inputs, 1, 5, and 6, and give us back a vector that has 1, 5, and 6 in it. There's also functions can do more complicated things, like the read.csv function takes a character string as input. So we had to put quotes. Oh, whenever you have quotes, you can either use single quotes or double quotes in R. They're synonymous. If we have myfile.csv, it will go on your file system, find that file, myfile.csv, read the table of data, and return a data frame as output. So this read.csv function is used to import data into R from external CSV files. That's also a function. Any questions? Okay, so that was a very brief intro. Now it's all kind of abstract, so let's actually do some hands-on stuff, and we will let me close that. We'll sort of go back and forth from now on between the slides and the console, the RStudio window, so that we can execute some code and then talk about what it is we did. So we're just gonna type code directly in the console now instead of running it off the script yet. So some of the most basic R code you could do is just to use R as a calculator. Plus, minus, multiplication, division, and power. We could use R as a calculator. So you could write 2 plus 3 in the console and hit enter. Let's try that and see what happens. So here you can see that down here I've got my cursor. There's a little sort of prompt here, and you can type 2 plus 3 in there. 2 plus 3. By the way, you can put spaces in your code to kind of separate things out and make it easier to read. So 2 space plus space 3 will give you the same result as 2 plus 3 with no spaces in it. I prefer to space things out to make it easier to read, but not everyone agrees with that. So I'll hit 2 plus 3 and then hit enter. Kazam, it says 5. Well, it doesn't just say 5, it says bracket 1, 5. So we use R as a calculator. We'll talk about what that bracket 1 means in a second, but hopefully you can see we've used it as a calculator. Pretty simple so far. The next thing we're going to do now, we might not just want to see that 5 printed on our screen. We might want to use that number later, the result of that calculation in future calculations. And the way we would do that is by assigning the result of some calculation to a named variable. So we're going to create a variable and give it a value. And we use the assignment operator, which looks like an arrow pointing towards the left. It's made of the less than sign and a hyphen. And so we give the name of the variable, assignment operator, and then the value. And we can read that as variable gets value. Variable names could contain, they can contain letters, numbers, periods, and underscores, but they can't contain spaces and they can't start with a number. And you can also use equal sign instead of this assignment operator, but that's just sort of more of a curiosity. For consistency, we're always going to use this assignment operator when we're going to create variables, because the more consistent your code is, the more readable your code is. That means the more reproducible your science is by others and by yourself in the future. It's just better for your science if you make your code very clean and very consistent. So let's go back to our RStudio. Okay, so here I've given you an example here. We're going to, every time there's 3 dots in the code, that's a blank for you to fill in. So whenever you see 3 dots, just delete them and replace them with the code that is on the slide. So if I get rid of those 3 dots and put that assignment operator in there, so that says x gets 2 plus 3. Okay, and now if I want to run a line of code from my script, all you have to do is if your cursor, the blinking cursor is anywhere on that line, you can either go up here and click the run button, or you can hit Control Enter or Command Enter if you're on a Mac. So either if my cursor is here on line 13 and I either click run or I type Control Enter, it will have the same effect. So I'm going to hit Control Enter. And I just ran this line. It says x gets 2 plus 3. But the 5, it doesn't say 5 anymore. Instead, it has defined a new variable called x in my environment, which has the value of 5. And if you have your environment pane up, you can see there's a new variable that's appeared there, x, and it has the value of 5. Instead of just printing 5, we've created a variable to be used later. And we can also, as I showed you, you could use the equal sign to create a variable. So y, I can put a space before it if I want to, equals 3.5 is the same effect. If I hit Control Enter, now I've got a new 2 variables in my environment. Y is 3.5. Okay? Now, if I do want to print the result of x to the console, I can just type x in my console and hit enter, and it will print that variable's value to the console. And here's just some examples here I have on the slide for things you can do with variables. If I just go to I'll put my cursor down here and just type x and hit enter, you can see it prints the 5. By the way, R is always case sensitive. If I type capital X, I get an error, object capital X not found, because it treats small x and big X as different. Now, if I execute this line of code here, x plus y, I can work with those two variables I've already defined and get a new result. So it will, if I run that line by either clicking run or hitting Control Enter, I'll get 8.5, right? Or I could do x times 4. X is still 5, so it prints 20. Okay, now another thing you can do with variables is you can update their value and sort of overwrite them with a new value. So x gets x plus 1. If I execute this line of code, what will x be after I execute this line of code? Anyone want? You can put it in the chat. What's x going to be after I say x gets x plus 1? Should have warned you, I'll try occasionally to have some audience participation. Anybody want to answer that difficult question? If x is 5 right now, and then I say x gets x plus 1, what will x be after that? I see people are saying 6. Okay, good. Excellent. Now, so if I execute this line of code, nothing prints to the console, but now x is 6, okay? And so if I say z gets x times 4, it's going to use that new value of x, 6, not 5 anymore. It's going to use 6, so z is going to be 6 times 4 is going to be 24. You can see now we have z equals 24. Pretty easy so far. We're kind of starting out slow. Let's see. Okay. Another thing that's important in code is that you can also, in your script, you can include comments. And those, if you run the entire script, the comments will not be evaluated as if they're code. They're just in there as notation to help you or others later remember what it is you did. And you put the pound or hash sign in front of the text, and then it will just be a comment. You can see I have put these sort of headings as comments, right? Like you could run this entire thing. Oh yeah, if you highlight an entire block of code, and then you can hit either run or Control Enter, it'll run it all at once. So it'll run the whole thing, but it just ignores anything after the pound sign as a comment. I showed you already that functions can take inputs, arguments, they're parentheses after the name of the function. And so that means that is the input to the function, it'll return some output. Like for example, log parentheses 1,000 will take the natural logarithm, not the log base 10, the natural logarithm of 1,000 and give us the output. Or sine, obviously another mathematical function. R has the constant pi predefined in it, so sine of pi and log of 1,000. We'll just do those just to demonstrate. Log of 1,000. Oh, by the way, if you start typing a function name in RStudio, it will pop up this kind of like dialog that will give you all the functions beginning with the letters LOG that you might want. And then it even pops up a little inline help on the function that you can go through, and you can press F1 to get the full help in the help window, but we just want this log function. You can hit escape or click on it to make that go away. And so we'll execute log of 1,000. There we have the natural logarithm of 1,000. And we can do sine of pi as well. And by the way, you can see it's 1.2 times 10 to the negative 16th. Really, sine of pi is 0, but computers use numerical approximations to do those type of calculations, and that's why it's not exactly 0. It's like the numerical algorithm is not perfect. We sort of you can set the defaults of how close you want things to be. But the default is basically getting you within 1 times 10 to the negative 16th of 0, which is good enough for most applications. Just a side note. I showed you already once, but we'll show it again, that functions can take multiple inputs, and we put commas between them. You can, and here we're going to use the function paste. Paste takes 2 or more character strings, text strings, and paste them together into one text string. Again, I've showed you that you can use either single quotes or double quotes to define a character variable. We're going to make a variable called my_name and give it a value. I put Quentin, but you could put a different name there if you want, and then we'll paste them together, a string that says hello, comma, and a string for the name, and those are the 2 arguments to paste. Let's do that. So yeah, my name, I'll put quotes, Quentin, hit Control Enter to run that. Now we have a character string variable defined called my name that has a value of Quentin. And then we'll paste the my_name variable together with hello, and the fully combined text string will appear in the console. Hello, Quentin. So, you know, that's an example of a function with multiple inputs. Any questions? This may be review for many of you, but I think it's valuable to make sure everyone's on the same page, because we'll be doing some kind of, you know, within a few hours from now, we're going to be doing like machine learning models and stuff. So if you don't have this down, then some of that won't make much sense. You can, while you're in your R session working in your console, you can type question mark followed by the name of a function, and that will pull up the help documentation for the function. By the way, you can use double question mark to search all the help documentation for any search string. I never use this because, you know, obviously we have Google, we have the, you know, Stack Exchange forums. God forbid we have AI large language models, which I would only use with great caution, but they are good for simple coding things. They're kind of perfect for that. So I rarely use this search function, but getting the help documentation for a function is very useful because it can help you quickly see what the names of the different inputs are and what they're supposed to do. So I'll just show that example for the paste function real quick. Go to your console, put question mark paste in there, hit enter. And then here in the help tab will pop up, and it will tell you what are the different arguments to the paste function and what they each mean. Now, I've showed you already that you can either have output print to the console, or you can have output assigned to a variable to use later. Well, some code does a third thing, which is produce side effects. Like it doesn't print things to the console or assign a variable, it does something else. And a very common example of that is any code that makes a plot has a side effect where it will display that plot. Well, I'll show you the plot function is the simplest way to make a plot. R comes with some built-in example data sets. One is called the MT cars, Motor Trend Cars. It's like the performance specs of a bunch of different car brands from the 70s from Motor Trend magazine. I use it a lot for example data sets. And so this MPG tilde HP, in this data, there's a column called miles per gallon and a column for horsepower. The tilde means plot a scatter plot with miles per gallon on the Y and horsepower on the x-axis. And which data set do those two columns come from? Data equals MT cars. So this is also on the side to note that sometimes function arguments have names that we tell it specifically which input is this. Well, the data equals means the that argument specifies the data set that we're plotting out of. So let's just see what happens when we run that plot function. If I put my cursor there and hit Control Enter, nothing comes up in the console at all, but I see there's kind of a scatter plot that is made off of this example data set in the plot panel in RStudio. There's also other things that code can print to the console besides the output. And there's 3 categories: errors, warnings, and notes. I'm going to show you an example of each of them. An error indicates that something went wrong in the code and no output is produced. Instead, the error is produced. For example, every time you open a parentheses, you have to have a close parentheses on the other side. If I try to run this code that has mismatched parentheses, we have only one opener but 2 closers, it will give me an error. So let's run that code and see what happens. Control Enter. Error, unexpected parentheses. So R tries its best to give us a informative error message that will explain why we can't do this code won't run and execute. Sometimes you get more confusing error messages, and kind of trying to decipher them is like an art. But that one makes sense. Very simple one. A warning: the code has still run and it still produced output, but it indicates the result might not be what you expected. And so the warning is kind of like R trying to be helpful and tell us, hey, we might want to take a closer look at this. Like if I take logarithm of -5, the log function in R expects a numeric input, but in mathematics, the logarithm function cannot take a negative input, right? Logarithm of is only defined for positive numbers. So let's see what happens when we try anyways to take log of -5. I run this line. I get NaN. That stands for not a number. That means that it's mathematically invalid. It says warning message, NaN's produced, right? And so that means, maybe this log is coming after a bunch of other calculations, and we didn't really know that negative numbers were produced. So the warning may help us go back and debug what the issue was, why we got negative numbers beforehand. But the code still runs. Errors stop if you run a bunch of code at once and an error is in the middle of it. Error will stop there and nothing below it will run. But if you have a warning, it'll keep going. Also, a lot of code produces notes, which is not an error or a warning. It's just other useful text. Like if the rep function means repeat a value that many times. If we want to make a vector of 100,000 zeros, we would say rep 0, 100,000. Let's say we just ran that and wanted to print it to the console. Well, it starts to do it, and then it gives you this note basically that says we have reached the maximum number of digits that you can print in an interactive session, and it's omitted 99,000, which is just trying to do for our own benefit, so you don't accidentally print millions of digits by mistake. And that's just like a little note, right? Everything worked fine. It's just a note. Yes, so that's an example of a note. Yes, I mentioned before, every time we returned a value, it always had a bracket 1 before the like when we ran 2 + 3, it didn't just say 5, it said bracket 1, 5. Well, that's because we were actually not just getting 5, we were getting a vector that is 1 element long, and that element had a 5 in it. And vectors are very common in R. They're any sequence of 1 or more elements of the same data type. Like if we have a bunch of numeric values, that's a vector of numbers, essentially, of numeric data. We could have a bunch of text strings, character vector. There's also factors and logicals, which are also common data types in R, which we will revisit later. So let's go into numeric data a little bit. How would we, there's just for example, let's say we wanted to make a numeric vector with a sequence of integers 1 to 100. Well, there's a function seq for sequence, which has 3 arguments that have names that we will submit to that function. Again, since we have multiple inputs, we separate them with a comma. From, to, and by. From means where does it start from? 1 is the lowest number in the sequence. 2, it goes to 100. That's the highest number in the sequence. By equals 1. We're going up by steps of 1. And just to show you that you can actually, if you want to just make a sequence of consecutive integers, you can use this colon as shorthand. 1 colon 100 does exactly the same thing as this code above. It will give you 1, 2, 3, all the way up to 100. Show you that. So if you type in seek for sequence, from equals 1, 2 equals 100, by equals 1, and then hit Control Enter, we get yes, 1 through 100, and you can see it's printed kind of like every so often it tells you where you are in the vector. So element 1 has a 1 in it, element 38 has a 38 in it, and so forth. And if I do 1 colon 100, hit Control Enter there, is exactly the same. Character, we've already seen character data a little bit. Let's look at it some more and make some vectors of character data. Again, we can use single quotes or double quotes around the individual elements in the character vectors. And this is, I also at this point wants to show you how to index vectors. And this can be done with character or numeric, any kind of vector. If you want to pull out individual elements from a vector, you may do that by using the square brackets after it and saying which elements do you want to pull out. So you can, oh, by the way, and this letters, R comes built in with a vector called letters, which has all the letters from A to Z, each as a vector with 26 elements long. So let's yes, if you use the C, first I just want to show you the C function, which is used to combine individual elements into a vector. So if we have A, B, C, D, E, F, G, this is going to make a vector that's 7 elements long that has, yeah, the first element will be A, the second will be B, and so forth. Hit Control Enter. So that's what we get there, 7 elements long. Now, I'm going to take this letters vector, which has A through Z. If I say letters 1 colon 7, that's going to give me elements 1, 2, 3, 4, 5, 6, 7 of the vector that has the alphabet in it. So it's also going to give me A, B, C, D, E, F, G. If I hit Control Enter, I get the same thing. We don't have to use consecutive numbers when we pull out a subset of elements in a vector. You can use the C function to get any elements you want in any order. So if I use 1, 18, 19, that means, okay, combine me the 3 numbers 1, 18, and 19 into a vector, and then use that vector to index the letters vector and pull out the first letter in it, the 18th letter in it, and the 19th letter in it, and put those into a new vector. Okay, so if I did 1, 18, 19, hit Control Enter, I get A, R, and S as a 3-element long vector that was made out of the 1, 18, and 19 elements of this original vector. Okay. These are just some things you want to keep in mind when you're working with numeric and character data. Sometimes you may be working interactively with data and not realize that you have sort of a mix of numeric and character data, and you may accidentally submit a character input to a function that is expecting numbers, and that's going to give an error because functions expect a certain type of input in order to give you output, right? Like logarithm has to take numbers as input, and so if you try to send a send a text value to it, it's going to give you an error, right? And for example, if I try to send hello to the log function, it will give me error in log of hello, non-numeric argument to mathematical function. Sort of self-explanatory there, right? Another important thing to know is that if you try to, for many functions, if you send a mix of numeric and character data to that function, it will force them all to be character data. Like it's when R makes a vector, every element in that vector has to be the same data type. And so if you, like, let's say you coded your missing values, for example, as just with the text missing or missing value, and then you tried to read that data in as numerical because most of the numbers in that column of data are numerical. Well, R is not going to know what to do because it's trying to make a vector out of this mix of characters and numericals. It's going to just do the only thing it can, which is force them all to be character, force them all to be text. Because you can store a number as text, but you can't store text as a number. So it's going to turn them all into text. Like if I run this, hit Control Enter on this line, you can see that it put quotes around the 100 and the 5.3 and everything because it forced them all to be character. This often comes up when you're reading data in from a spreadsheet, and there are ways to get around it, which we'll talk about later. Okay, so I think,
I have
Bauer,
a
you have a
question.
question. Go ahead.
Yeah. So if it says the variable like 3-indole acetic acid, right? So those together is as a one variable. So how do you input into the function?
You mean like a text that begins with a number?
Yes.
Like if you, so in your, sorry, give me your example again.
For example, it's a metabolic data, right? You'll see like 3-indole acetic acid, right? So in that case,
Yep.
you have to put as like characteristic or
yeah. So that will be it has, even if it's okay if character variables begin with a number. So that would still just be considered a character if it begins with a number. It's just, but that's just a text, yes. But if you, right, like if there was like, 3.5 and then there was like A after it would treat that as text. You would have to include additional code to strip away those letters and just get the numbers and then convert it to numerical if you had that mix of them in there, if you wanted to be numeric. Yeah.
Okay.
We can, maybe that would make more sense with more of an example later, but. Okay, so another really important data type I want to cover, which is a little bit harder to wrap your head around, but it's pretty important, is a factor. Factor variables look like character. They often look like text, but it's basically any vector of values that can only contain a certain set of predefined values or levels. The values, or they're called levels, and those levels are sorted in a specific order. And why would you ever want this? Well, you would often use it in a statistical model, like if you had an experiment you did where you had 3 treatments, low, medium, and high. You have a treatment column in your data. The only values it can contain are low, medium, and high. You want it to be sorted low, then medium, then high, right? So that would be, and then that, if you have it sorted that way and you have it set so that those are the only valid values in the treatment column, that will work better for the statistical analysis functions we will submit that data to later, and it will help reduce errors. Like if you have one where low was spelled wrong on one line of the data, it would cause an error or cause an issue, and you would be able to notice that because it didn't fit in with the only predefined values that vector can have. And so I just want to point out how are variables usually sorted when you make a factor. They're sorted in alphabetical order, and the first level when you do a statistical model is usually the one that's treated as the control or the intercept. So let's make a vector called treatment, and so we'll give it input of some text let's say we had 2 experimental units that were low, 2 that were medium, and 2 that were high. We have low, comma, medium, comma, high. Again, they're all in quotes because they're text. We use the C function to make a vector out of that. And then we use the factor function to turn that into a factor. And we'll make a new variable called treatment. Let's do that. So, right, we use the factor function, and as input to the factor function, we're going to use this C function. It's a vector of 6 character values. Hit Control Enter. We have a vector called treatment. It's a factor data type. So let's just type treatment in our console and hit Enter so we can see what it looks like. You can see it says low, low, medium, medium, high, high. And again, these are not in quotes because these are not character values anymore. They're a special kind of data type called factor that means, and you can see it says levels, high, low, medium. Those are the only levels that treatment vector can have. And you can see that it is sorted in alphabetical order. H comes before L in the alphabet, so it's high, low, medium. That doesn't make sense because we want it to be low, medium, high. You can override the default alphabetical order and give it your own order. And the way we would do that is we add an additional argument called levels, which and then we give a vector of the names of the levels in the order we want them to be sorted, and that will give us a sorted vector or it will sort the levels of the factor in that vector to whatever to that low, medium, high. So first low, then medium, then high. Okay, so we'll use the factor function again. So we'll take the treatment and that we already have, that vector, and use it as input again. So we're taking the factor, turning it into another factor, but with the levels sorted the way we want them. So we'll hit Control Enter. Yes, Bara.
So I have a question. So in the treatment, right? So what's the number behind that? Like, factor with 3 levels, low, medium, right? It says there is a specific number, right? 1, 1, 2, 2, 3, 3.
Yep.
So
yeah, so
what
it's
does
coding them as yeah, so now you see we've sorted them low, medium, and high. Yeah, so basically the way it is being stored in the way it's being stored is just as many unique numbers as we have levels. So it's being stored as 1, 1, 2, 2, 3, 3, but because it's a factor, the 1 is associated with low, 2 with medium, and 3 with high. Okay. So it's sort of a more efficient way to store data. If you know there's only 3 levels, it's just storing numbers and then a sort of lookup table to look up 1 equals low, 2 equals medium, 3 equals high. Yep, that's how factors work.
Okay.
So it can be useful if you want to sort things in a sort of predefined order. By the way, we have about 20 more minutes. I think we should be able to just about get done with this lesson by 10:45 Central, and then we'll take a break. If we don't quite get done, we can do a little bit more of it after the break and then start the second lesson. But yeah, so we'll have a break coming up pretty soon if folks are getting tired of this.
So Creedon, I have one more question.
Go
So
ahead.
when I click the code in my car, right, like that number changed. So it's gonna be changed for every time you do differently, like So when I ran the same code.
Sorry, go ahead.
So when I ran the code, like the 56 line, so the number is different in my global environment. So that's how it should be, like it changes every time.
Yeah. So if we run this, yes, this now it's back to being sorted high, low, medium, and since low is the first value in it, that's number 2, but that's not the way we want it to be sorted. So then once we resort it by running that line 58, it's now ordered low, medium, high. So low is the first level in the sorting order. That's why it's now a 1. Does that make sense?
Yes. Thank you.
Okay, cool. Okay, so I think, let's see, what do we have? We'll do a little bit on comparing and doing logicals, and then we're going to do some statistical distributions, and then something funny with packages. So those are the last three things we're going to do in this lesson. Oh, sorry, this slide got cut off a bit, but the other main data type you're going to be dealing with is logical. Logical is an even more specialized kind of data type than factor. Logical can only take two values. It can either be true or false. Why would you want that? Well, you often use it when you're doing comparisons of values and testing whether two things are equal or whether one is greater than the other and so forth. Anytime you do a comparison like that, you get a logical as your output. For example, the double equals equal is testing whether two things are equal. X equal y. Is X equal to y? The exclamation point equal sign is X is not equal to y. Yeah, you don't have to memorize all these. You can look these up, but if you use R a lot, you'll quickly learn them. You can use greater than or equal to, less than or equal to, and if you do multiple comparisons at once, you use the and or the or to separate them. I'll show you that in a second because the slide got cut off. So let me make a note about that. So let's do some of those examples. And now, and another thing is, if we do a comparison of an entire vector, it will do that logical comparison on every element of the vector, which I'll show you in just a second. So let's define a variable called x. X get 1:5. So if we remember that the colon is a shorthand for all consecutive integers between this one and that one, so x is going to be a vector that's 5 elements long. It's going to be 1, 2, 3, 4, 5. So I've hit Control Enter to define this vector of integers 1, 2, 3, 4, 5. If I want to say x equal 4, that will mean test every single element of x. Give me a true if it's equal to 4. Give me a false if it's not equal to 4. If I hit Control Enter, we get false, 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 true, false. Makes sense, right? Because it's only one of them is equal to 4. If we do exclamation point equal, that will give us x is not equal to 2. It'll give us a true if it's not equal to 2. It'll give us a false if it's equal to 2. We get true, false, true, 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 right? Because it gives it's not equal to 2 there, so it's false. We can do greater than, we can do less than or equal to as well, greater than or equal to, and so forth. So we can do, if you wanted to do greater than, x is greater than 3, it will test each element. If it's greater than 3, give us a true. So false, 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 true, true, because only 4 and 5 are greater than 3. You can do less than or equal to. That way, they'll only give us a true if it's less than or equal to 2. You can also do and or. That is a way to combine multiple comparisons into one logical result. X is greater than 1 and x is less than 5. So out of 1, 2, 3, 4, 5, which numbers are greater than 1 and less than 5? That's only going to be true for 2, 3, and 4. They're between 1 and 5. So we get false, true, 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 false. Makes sense. But what about if, and so that's the ampersand for and. For the or, we use the vertical pipe to say or. X is less than or equal to 1, or x is greater than or equal to 5. That's going to give us a true if it's less than or equal to 1, so 1, or greater than or equal to 5. So only the 1 and the 5 will be true. True, false, 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 true, right? The 1 and the 5 satisfied that condition. Everything else did not. This seems pointless now, but this is used, it's sort of the building block of a lot more complex things we might want to do with data that we actually want to do in the future.
Quentin,
Yes.
for mine, the x is greater than 1 and x is less than 5.
Mm-hmm.
It looks like I got true.
Is your X 1, 2, 3, 4, 5? If you just type X and hit enter, it should give you 1, 2, 3, 4, 5. Because we had a variable called X earlier. I think you might still have it in your
Oh, okay. Is
in your
that's
workspace there.
line 70? Line 70 you running?
Yes.
Or is it line
Yep,
70?
this one here. Yep. Yes.
Okay.
So just yeah, so sometimes you might just have a different variable defined than I do.
Okay.
Because if X is equal to 1, 2, 3, 4, 5, you should definitely get 5 values back when you do any type of logical on it.
Okay.
Then you get, yeah, so just make sure you run this line again. X gets 1, 5, and that will define X as 1, 2, 3, 4, 5 for you.
Okay. Thanks.
Moving on, the exclamation point is used as a negation operator. It will flip all trues to falses, and it'll flip all falses to trues. So we can put anything in parentheses after that. It will just flip them all. So if there's X equal 3, that'll give us true if X is 3, false if it's not. We can negate that and switch them all around. So not X is equal to 3, or yeah, we put whatever, but we get true, true, false, true, true, because it switched the trues to falses and vice versa. Another important operator we use to get logical output is the in operator, %in%. That is an operator that compares two vectors. It will go through the vector on the left-hand side, and it'll check the vector on the right-hand side and say true if any values here appear in this one, and false otherwise. So if X is 1, 2, 3, 4, 5, it'll say, okay, is 1 found in 1, 2, 3, 4, 5? Yes, it is. So true. Is 5 found in 1, 2, 3, 4, 5? Yes, it is. Also true. Is 6 found in 1, 2, 3, 4, 5? No, it's not. False. And 7 also false. We should get true, true, false, false. If we put this %in, % there, hit Control Enter, there's true, true, false, false. We can flip it around, and is X in 1, 5, 6, 7. So we'll say so X is 1, 2, 3, 4, 5, right? So we'll say is 1 in 1, 5, 6, 7, is 2 in 1, 5, 6, 7, and so forth. So we'll get true, false, 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 true, because 1 is, 2, 3, and 4 are not, and 5 is. That's what the in operator does. Everyone good there? Okay, so other functions. So far, we're looking at functions that have taken like one input. Some functions can take an entire vector as input and do something to each element of the vector and give you a new vector back with the same length. Like, for example, the exp function will give us the exponential, like e raised to the power of every element in the vector. And I also wanted to just demonstrate you a couple other things here. Well, first, we use this function setSeed, which means anytime we're going to produce random numbers, we can initialize the random number generator, so it gives us the same result each time. That's useful if you're doing simulations and want to reproduce your results later. We're going to make a vector called random numbers. rnorm means draw numbers, random values from a normal distribution. N equals 1,000 means we want 1,000 of them. We want the mean of that normal distribution to be 0, the standard deviation to be 1. SD equals 1. So we'll set, so that you should get the same numbers as I do if you set .seed. And this 1, 2, 3 can be any number. You can put any integer in there to set your random seed. You could use your zip code or whatever. So set seed, we'll do that. Then we'll use the rnorm function to make random a normal random draw, random deviates from a normal distribution. N equals 1,000. We want that many of them. Mean is 0. and SD, standard deviation, equals 1. I'll make a vector. So now you see we have a numeric vector called random numbers up here, which is 1 to 1,000. And I just wanted to show, then we can use the exp function exponential to say e raised to that power. And I just also want to show you this head function will use the exp of random numbers as input to the head function. And all that head does is display the first few values of a vector, just to make sure we don't print all 1,000. So if we run this, we get the first few values of taking those random deviates from a normal distribution and raising e to that power. If you set the same seed as me, you should get the same result as me. But if I set the seed to another number like 999 and do this all again, I got different random numbers this time, right? Okay. Other functions that take a vector as input only give you one or a few values. They're doing like summary statistics on your vector of data. Length is a function that tells you how many elements are in the vector. So it just gives you one value, no matter how long the vector is you put into it. Mean obviously gives you the mean of the vector. It just gives you one value, no matter how long is the vector. Same with median and SD for standard deviation. Those are examples of functions that would take a vector as input and give you one single value as output. So we'll do all that with random. Let me just set the seed to 1, 2, 3 again and redo this so we get the same. We'll all get the same result. Random underscore numbers. If we look at the length of it, okay, 1,000 is 1,000 elements long. The mean, again, it's giving us all the functions that begin with the letters MEAN. The mean is pretty close to 0, right? It's not exactly 0 because there's sampling error, but it came from a normal distribution with the mean of 0. Median should also be pretty close to 0. It is very close to 0. Standard deviation should be pretty close to 1, not exactly, but it should be close. It's 0.99. So those are all giving you one value. There's also some functions that take a vector and can return multiple values, like range. That will give you the minimum and maximum value in the vector. So it's taking a vector no matter how long and giving you a vector that's too long as a result. Range, and also quantile is a function that gives you quantiles of the vector, right? Like median is the 50% quantile, but we might also want like the 2.5 and the 97.5 quantile to get a 95% interval, for example. And so to do that, we use the quantile function. It has two inputs. The first input is a vector of data that we want the quantiles from. The second vector, we call it probs. Those are the probabilities that we want to calculate the quantiles for. So if we put 0.025 as the first element of probs, it'll give us the 2.5 percentile value from the vector. So like the value that 2.5% of the data are smaller than, right? And so it'll give us, if we put in 3 values for probs, it'll give us 3 quantiles back. So first we'll look at range to look at what the minimum and maximum we got are. So that's about -3 to +3, which is kind of what we'd expect from a normal distribution. We can do the quantiles as well. Probs. And if you know your rule of thumb that from a normal distribution, about 95% of the data are within 2 standard deviations of the mean, we should expect these quantiles to be roughly -2 and +2 because the standard deviation is 1. Not exactly, but it should be close. So you can see that the 2.5 quantile is around -2. There's the median again, and then this other quantile, 97.5 quantile, is about +2. Okay, I have only a couple of minutes left in this lesson, so I'm just going to knock it out, and then we'll take a break more or less on schedule. And of course, we'll have time for questions as well. This one, I don't have as much example code for, but I just wanted to tell you real quick, since R is a statistical programming language, it has a lot of built-in functions for statistical distributions. We just saw normal. There's obviously a lot more distributions. You know, you got Poisson, binomial, gamma. We statisticians love all our distributions. Well, a lot of distributions that are implemented in R have 4 functions that go along with them. They begin with R, D, P, and Q, and then the name of the distribution. Like the normal distribution has R norm, D norm, P norm, and Q norm. R norm we already saw, takes random draws from the distribution. D norm gives you the probability density function for the distribution. P gives you the cumulative density, and Q gives you the quantiles. I'll just show a slide showing what those are. And every time all those functions, right, distributions have parameters, right? Like normal distribution has 2 parameters, mean and standard deviation. By default, these functions will give you the mean of 0 and standard deviation of 1, but you can change any of those functions, have arguments mean and SD. You would supply your own parameters, and other statistical distributions have other parameters that are not called mean and SD, so those functions would have different arguments. So right, what is D norm? D norm, like for a normal distribution that's a bell curve, D norm tells you, D norm of 0 tells you how high the bell curve is at 0 on the x-axis. So like if 0 is on your x-axis, D norm will tell you the probability density function value, the height of the bell curve at that point. So 0 is the highest, it's the most probable value if you're drawing from a normal distribution with a mean of 0. So that's the highest value on there. P norm and Q norm tell you the cumulative probability of having that value or less. That's what P norm does. It's the cumulative density function, right? So 50% of the probability mass in the standard normal is less than 0. So if you do P norm of 0, you're going to get 50% back, 0.5. Q norm is the opposite. It's the inverse of that. So it's saying, if I have a standard normal, where will I be on the bell curve once I've passed 50% of the probability? Q norm of 0.5 gives you 0. So P norm and Q norm are inverses of each other. That's what that does. So we're getting a tiny bit into statistical theory, but this is just to kind of show you what those R functions do. Again, there's lots of other distributions, and you can type ? Distributions in your console, and that will give you help documentation for all the built-in distributions. And basic R has only a few distributions, and other people have implemented other statistical distributions in their own packages, which you can use if you don't find the distribution you're looking for in basic R. So what are packages? The last thing I'm going to talk about in this first lesson is packages. Oh, forgot I had a quick slide here about common mistakes that you might make and how you might want to think about addressing them. Well, here are some things you might want to check if you get an error in your code. Obviously, check the punctuation. Make sure if you start a parentheses, you finish it somewhere. If you start a quotation mark, you have to finish it somewhere. Those are obvious things to check. And RStudio will like flag your code if the punctuation isn't correct. So that's a benefit of using it. Spelling, a lot of errors you get by spelling the variable name wrong. Like if you defined a variable my_variable, then later in your code type my variable without the underscore, it's going to give an error because that's not found. Again, RStudio will help you, because if you sort of highlight a variable name, it will highlight all other places where it appears, so you can find those mistakes easily. Putting spaces in your code, it's good for making it more readable, but obviously you can put it like in between your assignment operators and in between your equations. Like this is exactly the same as this, but you can't put spaces in the middle of the name of a function or variable. Like you can't have a variable sum space numbers. That's going to give an error, but sum underscore numbers is fine. And as I already mentioned, R is case sensitive. So the sum function, which sums up all the values in a vector, will not work if you capitalize any of the letters of it. staff users are used to being able to put things capital, lowercase, however they want. Okay, the last thing we're going to do before we take a break is look at packages real quick. So far, we've only used code from base R, the set of functions that come with R pre-built, preloaded in without you having to go and get any packages. But almost anything you want, those base R functions do quite a bit. You can do some basic stat models with them and everything, but most of what you're going to do in R is going to require one or more packages, which are sets of functions that R users have contributed that are available to be downloaded from CRAN, which is like the repository of R packages centralized that manages all these packages. Again, they will check packages that are on there to make sure that they don't have any errors in them, but it's not a guarantee that the math and the stats in them is correct. So definitely you should prioritize using packages that have been around for a long time and that many people have used and cited in the peer-reviewed literature. I would say those are the ones that have the most reliable and good quality algorithms in them. Now, when you use a package, you have to install that package. You probably did this when you're getting set up for the workshop. You only have to install the package once, or anytime it is updated by the developer, you can reinstall it. But you really only have to install it once. You don't have to install a package every time you use it. And you can install a package. RStudio has a point and click dialog for it, but you can also use this function called install.packages. So we're going to install this funny package called cowsay to give an example of a package and how it works. Install.packages and put the package name in quotes as the argument. So the function is called install.packages. Hit Control Enter, and it will install the cowsay package, and which is used to make cows say things. So we'll give it a second. So it has to go find that package on the repository, download it, and kind of unpack it and install it. So it just did that. So I never have to run this line again. If I close R and start it again, I won't have to reinstall it because now the code of cowsay is saved onto my machine. But what I do have to do every time I use it is I have to load the package. That means pulling it up so that those functions in the package are available for me to use in my current session of R. The way you load packages is using the function library. I guess I don't know why it's called library. Basically, it will load it from the library of code that is on your local machine. So we'll hit library underscore or library parentheses cowsay. Hit Control Enter, it will load that package for us to use its functions right now. And back to the slides. Yeah, so this is what cowsay does. You can use the function say from it. You can put any character string in there, and it will make a cow say it. You can also use this by argument, by equals cow, because there's also other animals that you can make say stuff. We'll start with cow. So you can say USDA statisticians are the best, for example. So let's do that real quick. I can say whatever you want. Control Enter. There you go. Pretty cool, huh? So, and if you want to call up the help documentation for the function, you would type $say, hit Control Enter or hit Enter, and it will. Here are the. It gives you some a list of possible arguments to the by. A list of possible values the by argument can take. Like if we wanted to make a duckling say this, we could change by to duckling. Some of them are not safe for work, so yeah, but I'll do one that's like safe for work. There's a little duckling as well. Or what about a whale? That would be cool. There you go. I like this one. So anyway, that's another thing to note with packages. Now, since I loaded this package, I can use the say function without specifying what library, what package it comes from. If I wanted to specify because there might be more than one package that has a function called say in it, you can put the name of the package followed by 2 colons, followed by say, with the name of the function, and it will specifically make sure we use the correct version of the say function. Since packages are made by all different people, some of them have overlapping names, and this will make sure that it does exactly. If we had another package loaded that also had a say function, it might use the wrong one because it'll use the one that was loaded last by default. So this will ascertain that there's no conflict. Like if we want to say hello, a chicken saying hello, you could do that. Everyone good there? Okay, so now we'll oh yes, and another point is that you can say help package equals the name of the package in quotes, and that will give us the documentation for all the functions in a package. Like if we did that for cow say, help parentheses package equals cow say in quotes, it will give us all the functions in that package, and then you can click on one to get its documentation, like say. Okay. Yeah, that's all the hands-on stuff for lesson 1. Again, as you're learning R, you'll want to use, you know, as I said, I wrote this before AI large language models were a big thing. I still stand by using Google, and Stack Overflow is superior to using AI for help because it's actual humans produce that content. At least we hope so. And but for simple coding things, you can also use AI to help you. Also, the Stack Exchange forum is very good for questions about statistics, not specific to R. Statistics, data science, that kind of thing. I recommend. Yes, I think we already talked about that it's better to save code in a script and use again later. Console is just for playing around with stuff, but scripts are good to save your code to run later. And you should include your code with publications and presentations as well. So you always want to save it and not just run it once. I've only talked a little about functions. You may have heard of lists, if, else, for, all that kind of stuff. Yeah, those are important, but I would encourage you to look at the resources I have on my website for future reading, and a lot of classes and tutorials are out there, and you can get into that kind of stuff. And yeah, if you go to the full text version of the lesson, we have exercises. I put some sort of like homework if you want to later today or whenever. There's some exercises to practice what we've learned. Okay, does anyone have any questions or comments here at the end of lesson 1? Great, so we are just a little behind schedule. Let's take a break and let's come back at 10 after. So yeah, 12:10 by my watch, or 11:10 Central Time, and we'll do lesson 2 of this R bootcamp. I'm going to step out for just a moment, but I will be right back, and I will be able to answer people's questions during the break. So I'll stop the recording here so we have a separate one for each lesson.